In this video, I'm going to explain you about the definition of kernel and image and some related theorems with kernel and image. So first of all, let us explain about this. We have, first of all, we should have a mapping U to V, which is a linear transformation or vector space homomorphism. It's a linear transformation. It's a linear transformation or vector space homomorphism. Okay, now we'll try to define the kernel of F. So kernel of F is a collection of those elements from U. I collect elements from U such that it is mapped to 0 in V, so which is sent to 0. So I'll try to collect only those elements of U which is sent to 0. So that is the kernel of U. Okay, kernel of U. An image of F. Okay, I'm taking those elements f of x from V such that x belongs to U, and this image is also called the range set. Okay, this image is also called the range set of F. Okay, now so in this theorem we are going to prove this theorem here. So we are taking here U and V be two vector space over the field F, and F is a mapping from U to V, which is already a linear transformation. Then we have to show that the kernel F is a subspace of U and image F is a subspace of V. And the third one is that if F is 1, 1, if and only if kernel of F is equal to 0. So how to show a subspace? So suppose we have W is a subset of V. Then we say that W is a subspace of V if and only if I take two elements from W, okay, and I take two scalars from the field. If alpha x1 plus beta x2, if I can show these elements, this linear combination belongs to W, then W is said to be a subspace of V. So we are using this definition and will try to show that kernel F is the subspace of U. Okay, so I take two elements from kernel F. I'm taking two elements from kernel F and I take two scalars from the field. Now this element belongs to kernel F. So what is kernel F? It is a collection of elements from U which is sent to 0. So since this belongs to F, therefore what will have f of x1 should be 0 and f of x2 should be also 0 because these are belonging to kernel F. Now we have to show this linear combination belongs to kernel F. So to show that linear combination belongs to kernel F, we have to take f of this is 0. So I took here f of alpha x1 plus beta x2. This I have to show it is 0. So by using the first definition of linear transformation, we have f of alpha x1 plus f of beta x2. Okay, so by using the second definition of linear transformation, we can write this as f of x1 alpha into f of x1 plus beta into f of x2. So what is this? F of x1 is how much? We have 0 plus beta. F of x2 is 0, so you put here 0. So alpha into 0, we get 0 plus 0. So this is equal to 0. So we have shown it is 0. So this implies alpha x1 plus beta x2. This belongs to kernel F. So I have shown that it is in kernel F. Therefore, kernel F is a subspace of U. Now we'll try to show image F is a subspace of U. Okay, so to show image F is a subspace of U, V. Okay, we try to show that image F is the subspace of V. So what we'll do, we'll take two elements in V, image F. Okay, we'll take two elements in image F. So I'm taking small u and small v belongs to image F. Okay, and I take two scalars in the field. I'm taking two scalars in the field. So suppose I have a map. Let me draw a mapping diagram. Suppose this is u and this is your v, and I have a map F. So I'm taking image means from this set. Okay, so u is some element here and v is some element here. So there should be some element in u. Okay, there should exist at least x in u which is sent to u. Okay, and there should be another element y in u which is sent to v, since it is a mapping. Okay, so there exists xy belongs to u. Okay, xy belongs to u such that f of x is equal to small u and f of y is equal to small v. Now we'll take this alpha u plus beta v. Okay, alpha u plus beta v. This I have to show that it belongs to image F. Okay, so this is equal to alpha. What is u? U is f of x. So let me put here f of x plus beta v is f of y. Okay, now since f is a linear transformation, this can be written as f of alpha x plus f of beta y. Okay, again, since f is a linear transformation, f of alpha x plus beta y. Okay, now x is in where? X is in x and y is in u. Okay, x and y is in u and alpha beta is in f. Okay, so since u is a vector space, alpha x plus beta y will belongs to u. Since u is a vector space over the field F, alpha x plus beta y will belongs to u. Now this element is in u, so I take some element in u. Since we have a mapping, it will be sent to an element in v. So this element, f of this element will be nothing but in v, or we say that it is in image F. So this element belongs to image F. So I have shown here alpha u plus beta v belongs to image F. Okay, since this linear combination belongs to image F, this image F is a subspace of V. So I have shown here image F is a subspace of V. Now suppose the third Roman. Now let us take suppose kernel of f is 0. Okay, I take kernel of f is 0. I want to show f is 1, 1. Okay, so I'll take two elements in u. So I'm taking two elements in u. Xy belongs to u such that, okay, such that f of x is equal to f of y. My aim is to show x equal to y. If I can show x equal to y, then f is 1, 1. Okay, I can bring this one this side, so we get f of x minus f of y is equal to 0. Since f is a linear transformation, okay, since f is a linear transformation, this can be written as f of x minus y, which is equal to 0. So by definition of kernel, f of something is 0, that means this one should belongs to kernel f. So here we'll have x minus y belongs to kernel f. And kernel f is consisting of only one element, that is nothing but 0. So this implies x minus y should be equal to 0. So we have here x equal to y. So we have shown if f of x equal to f of y, we have shown that x equal to y, therefore f is 1 1. Okay, now conversely, suppose f is 1 1. Let us assume f is 1 1. Okay, we'll try to prove kernel of f is 0. So we have to show that kernel of f is 0. So I'll take one arbitrary element in kernel of f. So if I can show this x is 0, then we are done. Okay, so I take one element in kernel of f. So this implies what? Any element in kernel of f means this element is sent to 0. So f of x is equal to 0. Okay, so by using the property what we have proved already, f of 0, we have proved this already, we have proved this one, f of 0 is equal to 0. Okay, so this will be f of 0. Since f is 1 1, okay, now since f is 1 1, this implies what? X is equal to 0. So since f is 1 1, we have x equal to 0. So I took one element in kernel and I got that element is 0. Okay, since this is an arbitrary element and we got that arbitrary element is 0, therefore the kernel consists of only 0 element. Okay, so we have proved that if the kernel is 0, then f is 1 1, and if f is 1 1, then kernel of f is 0. And this kernel is also called the null space. Okay, this kernel f is called the null space. Of f. Thank you.